What does this say? It says for every x, there is a y that such that x plus y equals 0. What does that mean? It means it doesn't matter what x is, but y has to be a function of x. In particular, y is going to be negative x, right? So how do we condense that? Well, it's kind of written like here. There is some function y, namely y equals negative x, such that no matter what x you have, if you plug in x to the function to get negative x, then x plus negative x is 0, right? And what about this one? This says there's one fixed y, such that no matter what x you add to it, you get 0, right? One fixed y such that no matter one x you add to it, you're going to get 0. And that's just false, right? That's just not true, right? What about this one? This says there's one fixed y, so no matter what you add to it, you're going to get what you're adding to it, right? No matter what your x is, x plus your fixed y is equal to x. So that's what this says. There's one fixed 0, and for any x, if you add x to 0, you're going to get x. So that's true. The first and the last are true, and the middle one's not true. And this is our condensed way of saying it. All right, people buy that? How about this? This says there exists an algorithm such that for every input, the algorithm solves the problem, right? So here we're going to say solves problem P. There's a fixed algorithm that on any input, this fixed algorithm solves problem P on that fixed input, right? Here, we went through all of these, right? This says for any k you give me, I can come up with an algorithm that has that many of lines of code, right? So this says there exists a function that, given a number of lines of code, gives me an algorithm, right? So here's, for every k, there is some algorithm that has k lines of code. And no matter what the input and no matter what the k is, the algorithm that we get from our k is going to have k lines of code, right? What does this one say? It says, again, it says for every k there exists an algorithm. The same thing we said before, right? For every k, I can come up with an algorithm such that no matter what the input, the algorithm has k lines of code. That's as before. But we have a new thing. We also need that this algorithm solves the problem I, right, with these k lines of code. And that's no longer true, right? Because there are k's. If k's are so small, you can come up with an algorithm that had k lines of code, and you can come up with an algorithm that solves the problem, but it can't be the same algorithm, right? You can't come up with an algorithm with 2 lines of code that solves the problem. And what does this one say? Oops. This one says for every algorithm, there's a k, which is the number of lines of code it has, right? So you can choose any k you want. You can choose any I you want. You can choose any algorithm and any I you want, any input you want. And how many lines of code will there be? Well, there'll be some k lines of code, which depends on the algorithm, right? Given the algorithm, there is some k that will work. And that k doesn't depend on I, it only depends on the algorithm, right? And what does this say? For every algorithm, from every input, there's some algorithm that solves it, right? There's an algorithm that solves, right, for every input. We want to solve for every input, but the algorithm that we use to solve it can depend on the input, and that's bad, right? That's where we come into Clockwork Orange time, right? It's great to solve every input, but we don't want the algorithm that solves it depend on I, right? See why I have subscripts here is because I'm saying the algorithm depends on I, as opposed to the algorithm takes an input algorithm. You know, this is saying given an input, it tells me what the algorithm is. All right, so what about these guys, right? The first one says there's some fixed Turing machine that no matter what the input is, it solves the problem, and the running time depends on the input, right? That's what that whole line says, and it's what yellow says, right? Yellow says there exists. Oh, it's not a Turing machine; it's a Java program, right? There's fixed some Java program, M, blue M, that for every input it works, and there's the running time depends on the input, right? What does B say? B says you give me any binary input, you can map it, use B to map it over to an ASCII input, and the problem will give the same answer on the ASCII and on the binary, right? And what does C say? C says, you give me any Java program, red M, right? There, red M is our Java program. It's arbitrary, right? That's why it's red. You give me a Java program. Then I can come up with the Turing machine that's a function of the Java program, such that what? The Turing machine is a function of the Java program, and such that no matter what input I give it, the two give the same answer, right?